For lecture 6, we're going to begin the study of chemical reactions. This is chapter 4 in Wade. We're going to begin with something called the free radical chain reaction. So most of organic chemistry is the study of reactions. It's really the most interesting and useful aspect of organic chemistry. If you are an organic chemist by trade, your expertise is typically in the reactions of organic chemistry. So organic chemistry really is not a spectator sport. And what I mean by that is that reactions are constantly being studied, exploited, modified, even invented for use in the real world for very specific applications, maybe sometimes for industrial applications, usually with the end goal of building complex organic molecules in the lab. My goal for this course is to teach you how to be chemists, specifically how to think like a chemist, not how to be a chemistry student. So as we go through these reactions, we're going to try to cover 4 major concepts for every major class of reaction. We're going to look at what the overall reaction is, meaning what actually happens. We're going to talk about the mechanism, meaning the steps that the reaction takes to transform the reactants into the products. So basically how the reaction happens. We're going to talk about thermodynamics, so the energetics and equilibrium, to what extent the reaction proceeds. Does the reaction favor the products? Does the reaction favor the reactants? If the reaction does favor the reactants, how can we make it lean towards the products to get maximum yield, that kind of thing. And we're going to talk about kinetics, so how fast it happens. Now, in this course, you're going to probably learn hundreds of reactions. There are more reactions in organic chemistry than you can count. And as far as a summer course is concerned, far too many reactions to worry about memorizing. So although there is going to be some memorization in this class, we're mostly going to try to stick to rules, patterns, and trends to keep our information organized. And that's going to be our guide to help us understand and process and organize the massive amounts of information that you're going to be exposed to in the next several weeks. Let's begin with the overall reaction. Again, this is called a free radical halogenation. This is the only reaction that we can use on alkanes besides combustion. In lecture 1, we talked about functional groups. I wanted you to memorize a number of functional groups that were on that slide. And alkanes are typically not considered functional groups because you really can't do much with them other than burn them. The one thing you can do to an alkane is halogenate them by way of a free radical halogenation. So this reaction almost always involves adding a halogen, so usually a chlorine or a bromine, to an alkane, and in doing so, make what we call an alkyl halide or a haloalkane. So here's the overall reaction. In this case, we're going to start with methane. It's the simplest alkane. But remember, since this is a broad class of reactions, you can do this free radical halogenation to really any kind of alkane. We're just going to start with methane as a simple template to kind of understand what's happening here. So the reaction will take an alkane, in this case methane. We're going to react it with a halogen, in this case chlorine. We're going to react it in the conditions of heat or light. Usually it's going to be light. Heat is a fairly uncommon way of initiating a free radical halogenation. And what you'll notice is the product here is methane with a chlorine on it. And in place of the hydrogen that was on methane, we now have that hydrogen bonded to a chlorine. One thing to note here is that in organic chemistry, we often write reagents or solvents or some kind of reaction condition above or below the arrow. So again, our overall reaction is methane, an alkane, plus a halogen in the presence of heat or light, and you halogenate your alkane. Now, if you proceed to add more halogen, we can add a second chlorine to our methane, or under further halogenation, a third chlorine, or under further halogenation again, a fourth chlorine. And every time we add a halogen to our methane, we create a hydrogen halide as a byproduct. So looking at this reaction, what are some questions that you might ask if we're going to attempt to better understand this reaction? Think about that for a minute. So here are some questions that I thought might be interesting to know. We could ask, what does heat or light do to make the reaction proceed? Okay, so obviously, if we just have methane and chlorine without heat or light, this reaction wouldn't happen. This is a required condition. So what is the heat doing, or what is the light doing in order to make this reaction proceed? We could ask ourselves, why do we get a mixture of products? Why do we get one monohalogenated product or dihalogenated product? What's causing that? If we can understand why we get a mixture of products, we can maybe ask, can we do anything to ensure that only one specific product is formed? If we only want the monohalogenated product, how can we guarantee that we only make this product and not proceed further to the polyhalogenated products? If we do get multiple products, one question we could ask is, are the products formed in equal proportion? Do we make more monohalogenated product than dihalogenated product? Or if not, why do we make one product over the other? Is the monohalogenated product favored over the dihalogenated product? Or maybe is the tetrahalogenated product favored? If there are multiple products formed, are the major products formed because they're more stable? Or is it because they're formed more quickly? Or is there some other reason for that? To understand these questions, you have to do a number of experiments to kind of figure out what's causing the different effects that we're seeing. So here are some observations from experiment that helps us understand how the reaction is proceeding. First, that chlorination does not occur at room temperature in the absence of light. So we need either heat or light. Furthermore, the reaction only begins when light falls on the mixture or when it is heating. So we know now that the reaction requires some form of energy input to get it started. If we just mix methane and chlorine together, nothing happens. As soon as we add heat or light, the reaction begins. Secondly, we found that the most effective wavelength of light happens to be a blue color that turns out is strongly absorbed by chlorine gas, not by methane. The wavelength of light that is most efficient at initiating this reaction is absorbed by chlorine and not by methane. So that suggests that the light is being absorbed by chlorine, and from that step, something else is happening. So the chlorine is being activated in some way to initiate the reaction with methane. The third, here's an interesting term that you might not have heard of before, is that the light-initiated step, the very first step of the reaction, has what is called a high quantum yield. And this means that once you put, say, 1 photon of light into this reaction, once 1 photon of light gets absorbed by a chlorine, you get multiple products from that. You don't need to keep adding light, or you don't need to keep light on the reaction in order to keep it going. Once the reaction is initiated, it will keep going on its own, and you can turn off the light or remove the source of heat. You might remember this is called a free radical chain reaction, and that makes sense that once the reaction gets started, it is self-propagating. So this means that many molecules of product are formed from every single photon of light absorbed. There's a high quantum yield. This means that we need a mechanism, the number of steps or the sequence of steps that the reaction takes needs to explain how we can get many different individual reactions occurring from just a single photon of light being absorbed by chlorine. So let's look at the mechanism. Remember, we're going to go through the mechanism, we're going to go through the overall reaction, we're going to go through the kinetics, and we're going to go through the thermodynamics. So this is the overall reaction. It's a template. Now let's look at the mechanism. This is a 3-step mechanism. In a way, it's kind of like a 4-step mechanism, which you'll see in a minute. But classically, this is defined as a 3-step mechanism. We believe that the reaction occurs in 3 steps. The first step is that initiation step, where chlorine absorbs a photon of light, which we're going to often abbreviate as H nu. Remember, that's the formula for the energy of a photon of light. And what happens is that photon of light gets absorbed by the chlorine, and it causes the bond between the 2 chlorine atoms to cleave homolytically. What that means is that the bond splits symmetrically. So I've shown you this notation before. We're going to use arrows to denote the movement of electrons in a reaction. So these single-headed arrows, or these fishhook arrows, denote that we are moving a single electron. So if these 2 electrons are the bonding electrons between these chlorines, the absorption of a photon causes this bond to split symmetrically, homolytically, where one electron goes onto one chlorine and the other electron goes onto the other chlorine. In doing so, we produce 2 chlorine radicals. A radical, remember, is a species, an atom, that has a single unpaired electron. So this is a radical. So again, blue light, which we know to be absorbed by chlorine, but not by methane, initiates the reaction. And so we believe that initiation results from the absorption of light by a molecule of chlorine. It turns out that the energy of this chlorine-chlorine bond is about 242 kilojoules per mole, and that's approximately the right energy that is found in a photon of this blue light to cause it to split. And again, that's called homolytic cleavage because it's symmetrical. One electron goes one way, another electron goes the other way. So that's the initiation step. We've now formed our radicals. In subsequent steps, we don't need the light anymore, and I'll show you why. The second step is called propagation. Now, remember I said that sometimes you can think of this as being 4 steps. Propagation is really 2 steps in itself, but it is the propagation step, the first and second propagation steps, that explain how we get our product, explain how we get our halogenated alkane, and it also explains the high quantum yield. It explains how we can get many, many, many equivalents of product with only a single photon of light. So here's what happens. In the first propagation step, the chlorine radical that we produced in the first step grabs a hydrogen from our alkane. And this is how it happens. The chlorine donates 1 electron. The bond between the hydrogen and the carbon also donates 1 electron. In doing so, we make a bond between the chlorine and the hydrogen. The 1 remaining electron from that bond goes onto the chlorine. So in doing so, we have now hydrogen chloride, the chlorine and the hydrogen are bonded, and that 1 remaining unpaired electron goes onto the carbon. So now we have a methyl radical. We have essentially moved the radical from the chlorine to the carbon. That's what happens in the first propagation step. In the second propagation step, and this is probably the most important step in the reaction, that methyl radical reacts with an uncleaved chlorine molecule, a molecule of chlorine that has not absorbed a photon of light. Remember, once we've produced 1 chlorine radical, we can turn off the light and the reaction will continue happening. Here's how we explain that. The methyl radical donates 1 electron. The chlorine-chlorine bond donates 1 electron. And in doing so, we make a carbon-chlorine bond. That leaves the other chlorine in the molecule free with its one electron. So we have now added a chlorine onto our methane to make chloromethane, and we've regenerated a new chlorine radical absent of any more light. So you'll notice that this chlorine radical that we've produced in the second propagation step can go on to react with other unhalogenated methanes in another first propagation step. And these two steps can occur over and over and over in a chain reaction. The only time when this sequence of steps will stop is when we run out of chlorine to split, or we run out of methane to create our methyl radical. The third step is called termination. And the termination step really doesn't occur until the very, very, very end of the reaction. Once we've consumed all of our chlorine, we've split all of our chlorine into radicals, and we've halogenated all of our methane into either chloromethane or methyl radicals, there will be no more unreacted starting material left over, and all that we'll have left are radicals. So in the termination step, what happens is any two radicals combine, where each radical donates one electron to make a new bond, and in doing so, we make a product. So we could have a methyl radical combined with a chlorine radical to make chloromethane. We could perhaps have two chlorine radicals come together to make chlorine gas again. Or maybe we have two methyl radicals come together to make ethane, which would be a byproduct. So remember, once the only thing left are radicals, the only thing that those radicals can do is combine. If there aren't any non-radicals left, then the only thing that can happen is radicals can combine. So any combination of radicals that we have could combine to make some products. So you'll notice that we will indeed have some byproducts. This is kind of a messy reaction because we really can't control which radicals come together or how many of them come together or what combination of them come together. Here are some properties of the free radical chain reaction. The free radical chain reaction has a very, very large equilibrium constant. The KEQ is about 10 to the 19th. That's enormous. And what that means is that the reaction goes to completion, meaning that it will run until all of the reactants are consumed, until one or both reactions are consumed entirely. The reason this has such a large equilibrium constant is because it's extremely exothermic. The delta H, the enthalpy of reaction, is negative 105.1 kilojoules per mole. That's quite large, negative 25 kcal per mole if you're using the old-fashioned units. The entropy is also quite positive. 12.1 joules per mole K is pretty large for a reaction. I mentioned homolytic cleavage, that with that first initiation step, we split this bond symmetrically and we call that homolytic cleavage. That is defined as the bond dissociation energy. Basically, the energy of the bonds that are broken minus the energy of the bonds that are formed. So compare homolytic cleavage, in which we make free radicals. And again, that is the definition of bond dissociation enthalpy. It's the energy that is released or absorbed as a result of splitting a bond homolytically. And we mentioned that the chlorine bond being split homolytically is about 242 kilojoules per mole, and that corresponds to that blue color of light. The reason we use the bond dissociation enthalpy as the homolytic cleavage value and not the heterolytic cleavage value is because in heterolytic cleavage, when we're breaking a bond asymmetrically, for example, if we're going to take two electrons and put them both onto one atom so that we make an anion and a cation, in that case, the energy of that bond breaking is dependent on the solvent. If we've got a polar solvent, this splitting is going to be very good. It's going to be very happy because we're making charged species in a polar solvent. But if we've got a non-polar solvent, then splitting these two things into ions is not going to be very favorable. So you can't really define what the energy of a heterolytic cleavage is because it depends on what the environment is. On the other hand, if we're going to do homolytic cleavage, we have an uncharged species as our reactant and an uncharged species as our product. So whether we have a polar solvent or a non-polar solvent really doesn't matter. We're not developing charge anywhere. So this is really the true definition of bond strength. How much energy does it take to cleave a bond homolytically? So if you're curious about what type of light might be required to initiate a certain reaction, you can look up the bond dissociation enthalpy for whatever species you're trying to generate radicals on. Let's take a quick look at the reaction kinetics for free radical chain reaction. These are the two propagation steps. Remember that once we've initiated our reaction and generated our chlorine radical, that chlorine radical reacts with our alkane, in this case methane, to make the methyl radical and the hydrogen chloride in this case. That energy, the enthalpy, is positive 4 kilojoules, and the energy of activation is 17 kilojoules. In the second step, the second propagation step, the methyl radical reacts with an unreacted chlorine to make our halogenated alkane and regenerate our chlorine radical. And remember that that chlorine radical is now free to go participate in propagation step number 1. That second step has a reaction enthalpy of negative 109 kilojoules, very, very exothermic again, and a very small energy of activation, only 4 kilojoules. So remember from general chemistry that the step in the reaction with the highest energy of activation is the rate limiting step. It is the speed of that step in the mechanism that will determine the speed of the reaction. Here's a graph of that. Here's our starting material for our first propagation step. That has an energy of activation of 17 kilojoules and a reaction enthalpy of positive 4. That gets us to the products of the first propagation step and the reactants then of the second propagation step, methyl radical and chlorine. And that has an energy of activation of only 4 and a reaction enthalpy of negative 109. So we've gone up 4 and then down 109. So the overall delta H of this reaction is negative 105. So I'm going to zoom in on this graph here again. This is our first propagation step. This is our second propagation step. Looking at this in more detail, good question to ask would be, why is the methyl radical less stable than the chlorine radical? Think about this. Here we've got chlorine radical and methane. When we transfer the radical from the chlorine to the carbon, the reaction goes up. The reaction energy goes up. When we transfer the radical from the carbon back to the chlorine, once we halogenate our alkane, the reaction goes down significantly. So in both of these steps, propagation step 1 and propagation step 2, the methyl radical is less stable. Remember, chlorine is relative electron rich relative to carbon. Chlorine as a neutral atom, as a radical, has 17 electrons, whereas carbon only has 6. So if you think about a radical as being 1 electron shy of an octet, carbon is 1 electron shy of an octet, but he's only got 6 electrons natively. Chlorine being 1 electron shy of an octet, he has 17 electrons natively. So missing 1 electron is not such a big deal to chlorine because he's got so many electrons already. It's a much bigger deal to carbon to be missing an electron. So in all of these steps, having the radical on chlorine is a more favorable location for our electron deficiency. Now, remember that I said that this is a general reaction. It can work on any type of alkane. It doesn't have to be methane. We were just using methane as kind of a basic starting point. But I want to show you something very interesting. Let me show you propane. Here's a very interesting question. What if there are different kinds of hydrogens on the alkane that is being halogenated? By different kinds of hydrogens, I mean, let's look at propane. Propane has a primary carbon with 3 hydrogens and a secondary carbon with 2 hydrogens. And then we've got another primary carbon with 3 hydrogens. So you can think of this propane molecule as having 2 different kinds of carbons or 2 different kinds of hydrogens. We've got hydrogens on a primary carbon and hydrogens on a secondary carbon. And if we do a free radical halogenation to propane, we would get 2 different products, depending on whether we remove a primary hydrogen and put the chlorine on the carbon that's primary, or if we remove a secondary hydrogen and put the chlorine on the carbon that is secondary. We get 2 different products. This would be called N-propyl chloride or 1-chloropropane. This could be called isopropyl chloride or 2-chloropropane. Now, to understand what's going on here, let's think about some statistics. So there are 6 primary hydrogens. 1, 2, 3, 4, 5, 6. There are 2 secondary hydrogens. 2 right in the middle there. So if this reaction proceeded strictly based on statistics, there is 3 times the probability of putting a chlorine on one of the primary positions and only 2 times the probability of putting it on a secondary position. It's a 3-to-1 ratio, 6 to 2. If it was strictly statistical, we would expect to see 6 to 2 primary to secondary. But in reality, look what we get. In reality, we get 60% of the secondary product and 40% of the primary product. So although we would expect statistically a 3-to-1 ratio, we actually get a 2-to-3 ratio, primary to secondary. If you figure that out, you can cross multiply, do a little math here. You find that that means that these secondary hydrogens, in order to get a 60 to 40% ratio, while only having a 1-to-3 expected statistical ratio, means that these secondary hydrogens must be 4.5 times more reactive than the primary ones are towards chlorine. That's not necessarily something that you might expect to see at this point in the course. Another way to calculate it is that 40% of our product is being distributed through any number of 6 hydrogens. So that's 6.67% relative reactivity. And 60% of our product is coming from only 2 hydrogens. So that means 30% relative reactivity for the secondaries. So 30 to 6.67 is 4.5 times. So that's very interesting. You might not have expected that. A good question would be, again, if we have a mixture of products, why do we get one product favored over another? Let's see if we can figure that out. Here's a little bit of evidence. So here's our first propagation step. Once we've made our chlorine radical, we're going to take our propane. It's going to react with our chlorine radical, and the chlorine is going to grab a hydrogen. Is it going to grab a primary hydrogen to make a primary radical? Again, one of the 6 primary hydrogens would give us a primary radical. Or is it going to grab a secondary hydrogen to give a secondary radical? Only 2 hydrogens will do that. So let's look at some of these bond dissociation enthalpies. what energy does it take to break these carbon-hydrogen bonds? And what we'll see is that these are different. For methane, like we saw before, CH4, the energy that it takes to break a hydrogen-carbon bond is quite large, 435 kilojoules. It's really, really, really high. That's to make a methyl radical, to split this bond and generate a methyl radical. So if we let's look at making a primary radical. If we take one of these 6 primary hydrogens, split off the hydrogen and make a primary radical, it's now 410 kilojoules to do that. It costs less energy to make this product primary than it did to make the methyl. So this is a little bit easier, requires less energy, meaning that this product is a little bit more stable. Let's look at secondary. To take off one of these 2 secondary hydrogens and make a secondary radical, it only costs 397 kilojoules. 13 kilojoule difference between making a primary and making a secondary. If we go further and look at removing a tertiary hydrogen to make a tertiary radical, the energy is even less. It's only cost 381 to do that. So these bonds down here, the tertiary and secondary, are easier to break than the primary and the methyl. But in our case, what we're interested in is, why do we get secondary product and not primary product? Let me go back to the mechanism real quick. Notice that the carbon that loses its hydrogen, and therefore the carbon that gains the radical, is ultimately the carbon that receives the chlorine and gets chlorinated. So if our question is which carbon is going to get the chlorine, really what we want to ask is which carbon is going to get the radical. And what we can see here is that if our choice is a primary radical versus a secondary radical, it's easier to make the secondary radical. It costs 13 kilojoules less to split that bond to make the secondary than it does to split that bond to make the primary. So, okay, now we have a clue as to why we get this ratio. It's because it's easier to make the secondary radical. But again, why? We want to know why, what's going on. To put this graphically, again, what I'm saying is we're transferring our radical from our chlorine to our carbon. And when we do that, we're going to go up or down in energy. From our propane to make a primary radical, we end up here. From our propane to make a secondary radical, we end up here. That's a 13 kilojoule difference. So if our choice is which pathway are we going to take, well, we're pretty much always going to take the secondary pathway and end up at the secondary radical, because that gets us 13 kilojoules lower in energy. Just for reference, the methyl radical was up here, quite a bit higher in energy. So we have this order. Secondary is better than primary, which is better than methyl. So here's what's going on. This is super, super important. It's a concept called hyperconjugation for something that's maybe a little bit tricky, but let's look here. Here I'm going to show you a sp2 hybridized carbon. It's a carbon with only 3 bonds, not 4. And instead of that 4th bond, we've got an empty p orbital. So remember what the picture of an sp2 carbon looks like. It's a planar structure, trigonal planar, where the 3 bonds are being formed by the sp2 hybrids, and we've got an unhybridized p orbital sitting on that carbon. Therefore, it's a positive charge. If that carbon is adjacent to a tetrahedral carbon, which has, of course, 4 sp3 bonds, and so 3 other bonds besides the bond to the first carbon, it turns out that there is a little bit of overlap that is possible between the neighboring carbon's sp3 bonds and that vacant p orbital. And that overlap is a very good thing. Since that p orbital is empty, any electron density from neighboring groups that can kind of bleed into that vacant p orbital makes that orbital really not as vacant as it might seem, meaning that carbon becomes less electron deficient than it otherwise would be. Now follow what's going on here. Here's a vacant p orbital. So this is a cation. Now, we're not talking about a cation, okay? But we are talking about a radical. And a radical is still an electron deficient species. It wouldn't have a positive charge anymore. But instead of having 8 electrons, this radical carbon has 7 electrons around it. So it is still shy of its octet. So any adjacent groups that we have can kind of fill their electron density into that electron deficient orbital. So imagine that we just had 3 hydrogens around this carbon. So we have a carbon with 3 hydrogens. That's a methyl radical, CH3 with a dot. Those hydrogens have nothing on them. They might have an s orbital, but they have no other electron density around them. So they can't do anything. They cannot hyperconjugate, is the term, with this orbital. So a methyl radical gets no stabilization of its half-filled p orbital. In this case, this is a primary radical. If we have a methyl group, for example, next to our radical, this carbon is primary. It has one group next to it. So with a methyl radical, we have one source of hyperconjugation, one group that has some sp3 bonds that can overlap into that unhybridized p orbital and give it a little bit more electron density to fill it in. If we have another group, let's imagine that this hydrogen, instead of being a hydrogen, was another CH3 group like this. Well, now we've got 2 sources of hyperconjugation, and so we're going to get even more electron density bleeding into here. If we've got a third group, this third hydrogen, let's say, instead of having 1 C, we've got, say, 3 carbons around this central carbon. Now we've got 3 sources of hyperconjugation and even more stability. So for an empty p orbital, a cation, or a radical, which is still an electron deficient orbital, the more neighboring groups we have, the more overlap they can give into that empty orbital and make it feel a little bit more filled. That's a very good thing. Going back here, again, look, this methyl radical has no source of hyperconjugation. It's just hydrogens. And so there's no stabilization, which is why it costs so much energy to make it. But the more groups that we get next to this radical, here we've got one group. It's 2 carbons, but it's still one attachment to that carbon. That's primary. And it's a little bit easier to form that radical. Secondary has 2 groups next to that radical. And so both of these groups are filling electron density into that radical. And so it's a little bit easier to form it. We don't mind making it so much. In the best case would be tertiary, where we've got 3 groups, 1, 2, 3, that can all fill in their electron density into that central carbon and make that electron deficient carbon feel not so electron deficient. Now be careful, because what about an anion? If we have an anion, this orbital is now filled. This carbon already has 8 electrons around it. 2 in that bond, 2 in that bond, 2 in that bond, and 2 in the p orbital. Now, all of a sudden, hyperconjugation is a bad thing. We are now overlapping electron-rich groups into an orbital that's already filled. So A couple things are true here. The first thing is that hyperconjugation is bad for anions. The second thing that's true is that in reality, to avoid this overlap, to avoid hyperconjugation, this carbon would simply try to rehybridize itself to sp3. Again, we now have 4 valence shell electron pairs. So according to the Vesper theory, these should be at 109.5, not at approximately 90 degrees like we see here. So to avoid this negative overlap, this bad overlap, this carbon would just rehybridize to minimize that effect as much as possible. Okay, so here's our trend. Hyperconjugation says that a methyl radical is bad because there's no source of electron density to fill in that partially vacated orbital. Primary is a little bit better because we have one source of hyperconjugation. Secondary is even better. So we have 2 sources of hyperconjugation. And tertiary is best because we have a maximum 3 sources of hyperconjugation. So in a reaction, what you're going to do is you're going to look for the carbon that is the most substituted, because it is that carbon that will have the most high probability of forming that radical. It's easiest to break that carbon-hydrogen bond and make that radical. And ultimately, that radical carbon is the carbon that ends up with the halogen in the product. Here's another interesting observation in terms of selectivity. Here's the same reaction, propane, but instead of using chlorine, I'm going to use bromine, Br2. The reaction proceeds by the same mechanism. It's an alkane with a halogen in the presence of light and heat. Notice that we get the same products. We still can get a primary substitution and a secondary substitution, but now look at the ratios. Remember that with chlorine, it was 40% primary, 60% secondary. And with bromine, it's 3% primary and 97% secondary. All of a sudden, we have a very, very, very selective reaction. If we want to put bromine on the secondary position, we know that we can do that at 97% accuracy, 97% yield, with only 3% byproduct. With chlorine, we can only do that at 60% yield with 40% byproduct. So I'll walk you through the same math. Again, there are still 6 primary hydrogens that could lead to a primary product. There are still 2 secondary hydrogens that can lead to our secondary product. So again, if this was based only on statistics, we would expect 3-to-1 primary to secondary, because there's 3 times as many opportunities to end up with a primary radical than there is a secondary radical. But in reality, we end up with 3-to-97 primary to secondary. If you want to cross multiply that or figure it this way, if 3% of our product is derived from 6 hydrogens and 97% of our products are derived from only 2 hydrogens, if we figure that's 0.5% and 48.5%, we figure out what that relative reactivity is. Indeed, we find that in the case of using the bromine as our halogen, these secondary hydrogens are 97 times more reactive than the primary ones are. So we know already that secondary should be more reactive because it's easier to break that bond, because it's easier to stabilize that radical because of hyperconjugation. But what does bromine have to do with it, right? That's a great question. How come by adding bromine into the mixture, the secondary sometimes suddenly becomes way more favored than it was before? Again, it has to do with relative reactivities. If you want to ask yourself, why is something more reactive or why is something more stable? look at the product that is being formed as a result of that. Remember how I said comparing carbon to chlorine radicals? The chlorine radical was much more stable because it was already more electron rich. Chlorine has so many more electrons already than carbon does that missing one electron is not such a big deal. Well, it's the same with chlorine versus bromine. Bromine has 35 electrons in its radical form, and chlorine only has 17. So if one of those is going to be missing an electron, one shy of an octet, which one's going to be more happy? Well, it's going to be bromine. Bromine has so many electrons that it doesn't really miss that extra electron. So comparing bromine with our propane, here's the relative energies of bromine radical with propane to chlorine radical with propane. So you'll notice that from our first propagation step, where we transfer the radical from the bromine to the propane, we're going up in energy in both cases. Whether we make the secondary radical or whether we make the primary radical, it's still 13 kilojoules of difference. Again, that should make sense. It shouldn't matter whether bromine is around as to whether which carbon is more stable or less stable. That shouldn't matter. That's still that 13 kilojoules of difference between our primary and our secondary. But since they are both up in energy relative to where bromine is, this reaction is always going to take the lower energy route. If we're going to go up in energy in either case, we might as well go up in energy as little as possible. But look at where this reaction is relative to chlorine. So in case of chlorine, both of these products, or intermediates as they were, both of these intermediates are down in energy relative to chlorine. So if we go from chlorine radical to primary radical, or chlorine radical to secondary radical, they're both better. So we are going to be less selective. Chlorine doesn't care so much about what its first step is because in both cases they go down in energy. Bromine, however, has to go up in energy in both cases. So it's going to be very selective as to which carbon it transfers its radical onto. An analogy I like to use sometimes, kind of a funny analogy. Imagine that, let's say you drive a really fancy car, like let's say you drive a Rolls Royce, and you are forced to choose between driving a Ford or a Chevy. Since both of those cars are a step down from your Rolls Royce, you're going to be very picky about which car you choose. That is like bromine. Bromine is the Rolls Royce. He's very, very, very happy. He's very, very stable with his radical. If he's going to give up his Rolls Royce and choose a Chevy or a Ford, he's going to be very picky about which one he chooses. He's always going to choose the very, very, very best one he can pick. He's always going to pick the secondary radical. On the other hand, if you're chlorine, let's say that if you're chlorine, you don't have a car at all, and you get to choose between a Chevy and a Ford. Because you don't have a car, both the Chevy or the Ford are going to be awesome choices for you. You're going to say, you know what, I'll take whatever car I can get. I don't even care whether it's a Chevy or a Ford. I don't care if it's great or not so great. I'm just going to take the car. That's chlorine. Chlorine is going to take whatever step it can to give up its radical and transfer it onto the carbon, which primary and secondary are more stable than the chlorine radical. So let's do a quick review before we move on. We're almost done with the details, the nitty-gritty of the free radical chain reaction. But let's do a quick review here. So the order of stability for radicals on carbon is methyl, then primary, then secondary, then tertiary, from least stable to most stable. And that has to do with the amount of hyperconjugation that the product radical has. Methyl has no hyperconjugation, so it's not stable, so it's difficult to break that bond in the first place. Primary has a little bit more hyperconjugation. It has one source of hyperconjugation. Secondary has two sources of hyperconjugation. Tertiary has three sources of hyperconjugation. The more hyperconjugation you have, the more stable the radical is, meaning the easier it is to form in the first place. Remember from the mechanism, the carbon that loses its hydrogen, that is to say, the carbon with the weakest carbon-hydrogen bond, is the bond that's going to get split. That's the carbon that's going to get the radical. That's the radical that's going to hit the chlorine. And so ultimately, that carbon is going to be the one that gets halogenated. So you can always predict which carbon in an alkane is most likely to get the chlorine or most likely to get the halogen. It's the one that makes the most stable radical. Methyl, primary, secondary, tertiary is the order. The second aspect of the reaction is the selectivity of the halogen. Remember that in the case of chlorine, it was about 60% secondary, 40% primary. In the case of bromine, it's 97% secondary, about 3% primary. Now, you might be wondering, what about fluorine and what about iodine? Because those are the only other halogens that we really would ever react with. So fluorine is more like chlorine. Again, if you look on the periodic table, anything that chlorine is like, fluorine is more extreme. It's higher up on the periodic table. So whereas chlorine is a little bit selective, it goes about 60% secondary, 40% primary, fluorine is almost not selective at all. The fluorine radical is really, 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 really reactive. And so what you end up with is a huge mixture of products. You get no selectivity of primary, secondary, tertiary, but you also get very, very easily polyhalogenated products. So you get fluorines all over the place. Fluorine's a very, very difficult reagent to work with. And so these free radical halogenations are almost never done with fluorine. On the other hand, iodine is more like bromine. It's the kind of more extreme version of bromine, where its radical is so stable relative to the stability of the carbon radicals. If chlorine is up here and bromine is down here, remember fluorine might be way up here, and so it's so far downhill that there's not selective at all. Iodine would be way down at the bottom, so it would be so stable that it doesn't even react. So we kind of have a Goldilocks situation here where fluorine is way too hot, way too reactive, and iodine is way too cold, way too unreactive. Right in the middle, we have chlorine and bromine, and they're pretty good at being reactive enough to give a decent amount of product, but not so reactive that we can still control it and get a predictable product. So those are the two facets of free radical halogenation. I want to change gears just a little bit. We're still going to keep it in the context of the free radical chain reaction, but I want to talk about something called the Hammond postulate. This is something that's very kind of interesting. It gives you a very interesting insight that you might have not have thought of before when we look at these, say, energy diagrams. So let's look at this diagram here. We've got an endothermic reaction here. So we have our reaction coordinate from the beginning of a reaction. In this case, it's a mechanism. It's a mechanistic step from our first propagation reactants to our first propagation products or our second propagation reactants. Reaction coordinate on the x-axis and energy on the y-axis. This is an endothermic reaction. You can think about energy as being on the y-axis, but think about structure as being on the x-axis. This is really as we're changing the structure of this. Let's look at the transition state, this highest point in the curve is called a transition state. And that's basically the point at which, once you pass that point, you're destined to end up at your product. And before you reach that point, you are destined to end up back at your reactants. So that's kind of the point of no return, that transition state. And you'll notice something very interesting if you look at an endothermic reaction versus an exothermic reaction. What you'll notice is that the transition state is closer to the products in terms of energy. Okay, so on the y-axis, the transition states are closer to the products than they are the reactants. They are closer in energy on the y-axis. They are also closer in structure on the x-axis. In an endothermic reaction, the transition state is closer to the products than it is to the reactants. In an exothermic reaction, it's the opposite. You'll notice here's our transition state, and the transition state is not only closer in terms of energy on the y-axis, it's also closer in terms of structure on the x-axis. So it says here, in an endothermic reaction, the transition state is closer to the products in energy and in structure. In an exothermic reaction, the transition state is closer to the reactants in energy and structure. Transition state close to products, there's a large difference in the energy of activation between the reactants and the products. Between the reactants and the transition state. In the exothermic reaction, there's a small difference between the energy of activation and the reactants. So Hammond postulate says related species, meaning, say, a transition state between reactants and products, these would be related species. They are part of a reaction energy process. Related species that are closer in energy, meaning closer in terms of the y-axis, are also closer in structure, meaning closer in the x-axis. The structure of a transition state resembles the structure of the closest stable species. So if this is what the transition state looks like, we're going to draw something that the bond is broken from the hydrogen to the carbon and being formed between the hydrogen and the bromine. Since this is an endothermic process, our transition state should look closer like our products. The hydrogen should look a little bit closer to the bromine than it should to the carbon. So for an endothermic step, the transition state does not occur until that bond is almost completely broken between the hydrogen and the carbon and is almost completely formed between the hydrogen and the bromine, or the hydrogen and whatever halogen we're talking about. In this case, since it would be an endothermic step, this is going to be a bromine. Remember that bromine was going up in energy to get to our carbon radical. In an exothermic process, that would be for a chlorine. So if we are chlorinating, we're going to be going down in energy from our chlorine radical to our carbon radical. And so if it's exothermic, our transition state should look closer to our reactants. So our transition state should have the hydrogen closer bonded to the carbon and less bonded to the chlorine. Okay, one more note on hyperconjugation. We've already noted that radicals and cations, which are electron deficient species, are more stable when they have more groups around them. They are more substituted. That, again, is because of more hyperconjugation. That is true for cations. It's true for radicals. And remember, we said that it was the opposite process for anions, the opposite order for anions. Another way to kind of look at this, if you imagine that here's our carbon with our empty p orbital, it's a cation, or perhaps it's a radical maybe if it's a half-filled orbital. We've got these three groups around it if it's tertiary. that can donate electron density into that carbon. So that carbon doesn't really feel so positive because he's got all this electron density around it. So we have cations and radicals, but there are other types of reactive species. Besides cations and radicals, we also have anions, carbanions, and something called carbenes. Carbenes are an interesting species because they are formally neutral. That carbon, if you calculate its formal charge, remember 4 valence electrons from carbon minus number of bonds, which is 2, minus number of lone electrons, which is 2. So this is formally neutral. It has a formal charge of 0, but it's actually a very, very reactive species. It is both nucleophilic because it has a lone pair that it can donate. It's also electrophilic because it does not have an octet. It's kind of a weird species because it doesn't have an octet, but it's neutral. So in terms of hyperconjugation, you can kind of understand whether these species are going to be stabilized by hyperconjugation. Since cations and radicals are electron deficient, they should be stabilized by hyperconjugation. Carbanions, because they're electron rich, should be destabilized by hyperconjugation. Again, imagine that this orbital is filled. We're going to be donating more electron density into it, and that would be a bad thing. The order should be opposite for carbanions. So least stable would be tertiary, and most stable would be methyl, because methyl has no source of hyperconjugation. It leaves this carbon with as much electron density as it can handle already. The carbenes don't really have a preference for hyperconjugation. They can be stabilized by hyperconjugation. They could be destabilized by hyperconjugation. It kind of depends on the context, so don't worry about that too much. But generally, this is the order. For electron deficient species, tertiary is best, methyl is worst. For electron rich species, methyl is best, tertiary is worst. There are a couple other additions that I want to make. This position that I'm pointing at right here is called the allylic position. And it turns out that the allylic radical is even more stable than a tertiary radical. Even though technically speaking, this is a secondary carbon. There's only 2 carbons bonded to it, one there and one there. So the 2 hydrogens on it would be considered secondary. But because that radical is adjacent to a pi bond, we can draw a resonance structure. We can take 1 electron from that radical, 1 electron from the pi bond, and split that pi bond homolytically to put the other radical on the other carbon. We have now delocalized the radical through resonance. And that is a greater stabilizing factor than hyperconjugation. Resonance is a more stabilizing factor than hyperconjugation is. So allylic is a carbon that is adjacent to a double bond. That's called the allylic position. And so in a free radical halogenation, if there is an allylic position, that will take preference for the reaction over tertiary or secondary or primary. Even further, this is called the benzylic position. And the benzylic radical is even more stable than the allylic radical. So even though you might look at this carbon and say, well, that's primary because he has 1 carbon attached to it, so those 3 hydrogens would be considered primary hydrogens. They're really not, because the radical that forms when you remove one of those hydrogens can be delocalized the same way that the allylic radical can be. We can take 1 electron from that radical, 1 electron from the pi bond, make a new pi bond, and take the remaining radical and put it on the other carbon. We can do that 3 times. We can delocalize it once, and then a second time, and then a third time again. So again, more delocalization from resonance means that neither one of these carbons is ever fully electron deficient. It's only partially electron deficient. It shares that burden with all these other carbons. 1 carbon, 2 carbon, 3 carbon, 4 carbons share the burden of that radical. And so that's even better. So benzylic will take priority over allylic because they are resonance stabilized, and benzylic is more stabilized than allylic. And allylic will take precedence over tertiary, which will take precedence over secondary, which will take precedence over primary. Let's work on a few practice problems. I have one here. It says, predict the major and minor products and provide a mechanism to explain the formation of the major product. Why is this product the major product? So here we have an alkane, and again, this is drawn in line angle structure, so it's your responsibility to understand what this notation means and what the structure represents. And we're reacting this alkane with bromine, Br2, in the presence of light. So this is a free radical halogenation. And our job is to figure out what the major and minor products are. So thinking back over the course of this lesson, what was important in determining how we were going to arrive at the product? You can think of some of the rules we learned, some of the patterns we looked at. You can also think through the mechanism and figure it out step by step to get from the starting material to the product. I'm going to work this out right now in front of you so you can see step by step how I get from the starting material to the product. So I'll work through the mechanism, and in doing so, we'll get to the major and minor product. However, I want to caution you not to rely strictly on the mechanism in order to get to the product. I want you to think the big picture as well as the details. Part of the reason why is that on exams, if you need to work through the mechanism every single step in order to figure out the answer to a question that's only asking you about the product and not really asking you about the mechanism, you're going to waste lots of time drawing this stuff out. I want you to be able to get right to the answer by applying the rules and the trends without necessarily having to get to the mechanism. However, again, I might ask you explicitly to draw the mechanism like I am here. In this case, I'm asking you to draw the product, the major and the minor product, as well as the mechanism. So if you'd like to give this a shot on your own before I go through it, go ahead and pause the video right now, and you can do that. Otherwise, let's get started. So here's how I apply our patterns and our rules to figure out what our product is going to be. Remember that the more stable radical will result in the major product. So my job when I analyze this is to figure out where is the most stable radical going to be. And remember that we saw the trend that said that the more substituted the radical is, the more stable it is. So I want to look at the types of hydrogens I have here. Let's look at this structure. Where are our hydrogens? So I'll draw in some of our hydrogens. We've got 3 hydrogens right there, and those are primary. Those are primary hydrogens. They are on a primary carbon. We've also got 3 hydrogens here. Those are also primary. They're on a primary carbon. We've got 3 hydrogens here. Those are primary. They're on a primary carbon. Remember that the carbon bonded to one other carbon is a primary carbon. So these are primary hydrogens. We've got other types of hydrogens though. We've got 2 hydrogens here, and those are secondary hydrogens because they're on a secondary carbon. And then we've got 1 hydrogen right there. And that's a tertiary hydrogen because he's on a tertiary carbon. So remember that in the process of the mechanism, We're going to form a radical by removing the most reactive hydrogen, the one whose bond is easiest to break, requires least amount of energy input. So the trend was that tertiary was the best, that making a tertiary radical gives us the most hyperconjugation, so it's the most stable. So in this reaction, what I'm going to do to get to the major product is I'm going to think through, we're going to remove the hydrogen from the tertiary position, create the tertiary radical, then the radical is going to add to the bromine. And so ultimately, our major product should have the bromine in the tertiary position. So I can get straight to the product without even writing the mechanism. I'm just going to draw our structure, and I'm going to put a bromine in the tertiary position. There we go. That's the major product. There's a major product. Now, what would be the minor product? So the minor product would be the product that is formed in least quantity, or at least in lesser quantity. So what's not quite as good as tertiary would be our secondary position. So we could add a bromine to the secondary position. That would mean that we have our structure. But we're going to substitute one of the hydrogens with a bromine in the secondary position. That would be a minor product. And recall that in propane, the difference between a secondary and a primary was 97% to 3. So if you're thinking, okay, what's going to be tertiary to secondary? It's probably going to be even more selective than that. So this might even be 99% of the tertiary product and 1% of the secondary product. And then we'll figure that because bromine is so selective, it's not even going to bother with the primary products. So let's draw the mechanism. I said, let's draw the mechanism to explain the formation of the major product. So let's do that. Let's think through the mechanism. So the first step of the free radical mechanism is that the bromine gets split by light. So let's draw that. I'm going to start with bromine, Br2, and I'm going to exaggerate this bond here. I'm going to make that really long so that I can show the arrows. Remember, we want to show the curved arrow formalism that shows the movement of electrons in this mechanism. So I'll do that, but first I'll draw in our reaction conditions. It's Br2, and our reaction requires light to get started. And our curved arrows, I'm going to use red just to kind of separate that. We're going to show one electron going on to one bromine and one electron going on to the other bromine. That is the homolytic cleavage. And I'm just going to write under the arrow here in a different color. I'm just going to write an I for initiation to say that this is the initiation step of the mechanism. You don't necessarily have to do that unless I explicitly say label each step with a name or label each step. So I'll just do that for now. And what is the result of the initiation step is that we make two Br dots, bromine radicals. I'm going to move this down to give us a little more room. There we go. Okay, now that was the initiation step. What's the next step? Remember, the first propagation step comes next. And in the first propagation step, the bromine radical reacts with our alkane. So I'll draw in our alkane. And the way it reacts with our alkane is it donates an electron to break the most reactive carbon-hydrogen bond. And remember, in this case, that's our tertiary. So I'm going to explicitly draw in that hydrogen. There we go. And again, I'm going to kind of elongate the bond just so that it's really easy for us to draw this in. Move this down. just a little bit. And let's go ahead and draw in our arrows. So remember that the bromine radical is going to donate 1 electron, so we'll do that. The bond is going to donate 1 electron, and the other electron is going to go down onto the carbon there. So that, I'll draw our arrow. I'll turn the corner here. We'll go down like that. And let's draw the product of that. We should have our alkane, like that. But we have a radical now. We removed that hydrogen. So let's draw the dot in there. That dot, again, represents the unpaired electron that's left over. And a byproduct, I'll also write that in parentheses down here, plus HBr. Remember, that's not particularly important. It's a byproduct. It's not organic. So you might want to include it if you want to be thorough, but it's really not the focus of this reaction. Okay, now I'm going to draw in pink again. I'm going to just write P1 to say that's the first propagation step. Okay, and that's the result of our first propagation step. We've made our alkyl radical. It's our tertiary radical. All right, now it's time for propagation step 2. Remember what happens in propagation step 2? Our radical reacts with an uncleaved bromine molecule. So I'll draw in our bromine molecule. Actually, I'm going to move it just so we get a little bit more room. There we go. And let's draw in the arrows. Remember that the way it works is our radical is going to donate 1 electron. Our bond is going to donate 1 electron. So those are now connected. And we're going to leave the other electron on the other bromine. So now we get to our product. Remember that the second propagation step we said is kind of the most important step because it does 2 very important things. It first of all generates our product. It generates our brominated alkane. But it also leaves us with 1 bromine radical. And that bromine radical is free to go back and react in propagation step 1 so that we have our chain reaction. So over or under this arrow, we'll just write P2. Remind us that that's our second propagation step. Now, we could draw any termination step we want. If I ever ask you to draw a mechanism, I'm just going to let you pick a random, not a random, but I'm going to let you pick a single termination step. You don't have to draw every single possible termination. I'm going to draw a tricky one just so that you can see kind of the process of this. Remember that the termination step is one where any 2 radicals come together to make a neutral molecule. That, again, once all of the neutral molecules are chewed up by the radicals, the only thing we'll have left are radicals. So at the end of the reaction, we only have radicals left to deal with. So I'm going to choose 2 alkyl radicals. I'll write down here, I'll just say our termination step. We'll do our termination step. And I'm just going to choose 2 alkyl radicals. So we'll take 1 alkyl radical. There, it's going to be tertiary. And we'll take another one. In fact, I'm just going to copy this. And let's show these two coming together to make a neutral molecule. So we'll take this radical is going to donate, and this radical is going to donate. And so they're going to make a bond. Now you notice that this is going to be a pretty tricky structure. So watch how I do this. What I like to do is I like to draw one of our pieces exactly in place. So I'll draw our left structure exactly in place. Now what I'll do, I'm going to use a different color here just so you can see. I'll use green. Here's the bond that we're forming. There's a new bond. Now, that bond is going to be connected to this carbon right there in orange. So that is going to be right there. Now, let's look at what is connected to the orange carbon. Over here, we've got two methyl groups. I'll just highlight that in light blue. There's a methyl group, and there's a methyl group. So let's draw those two methyl groups on this molecule attached to this orange atom. So there's a methyl group, I'll go up. There's a methyl group, I'll go that way. Again, we're going to try to maintain these proper angles because they represent a tetrahedral structure in real life. The other thing that's attached to this orange carbon, but beside the two methyls, is this ethyl group right there, two carbons. So let's add that. We'll go 1, 2. There we go. There's our product that we get by combining our first radical, which was in dark blue, with our second radical in light blue, connected with the green bond, that's the bond we made, between the two tertiary carbons. So there's your answer. There's our mechanism. We first analyzed the starting material. We figured out the big picture. We used our rules and trends and our pattern to determine what the final product should look like without even having to draw the mechanism. But then we went through and thought out step by step, how do we get there? How do we explain the formation of our product, our major product, right there, using a mechanism? And we did 3 steps: initiation, propagation 1, propagation 2. That explained our product. And just to be thorough, I also included a termination step, and I picked the tricky one just so you could see how I did that. If you want some extra practice with naming, you could name our starting material. You could name our products, the major product and the minor product. And you can also name this byproduct right here, our complicated byproduct. Figure out what that name is if you want practice naming. Here's our second and final practice problem. This one's a little bit more tricky. Hopefully you understood the first practice problem you did, and you're up for this challenge. This says the following reaction gives rise to 2 major products of approximately equal stability. So 2 different products that are so similar in stability that we're just going to call them both major products. And I want you to provide a mechanism to explain the formation of both of these products. So again, I'm going to you can pause the video and try to work through this on your own. If you don't want to wait, you can just follow along with me here, and I'll walk you through the steps that I would take to get to the answer. So to do that, again, let's think about the big picture. We want to identify the hydrogen that's going to get removed in order to give the most stable radical possible. So let's analyze our structure again and figure out what type of hydrogens we have. Now, I threw in a double bond here, and that should be kind of a red flag, because if you recall, when we looked at the stability of different types of radicals, the double bond gave us resonance structures. If we created a radical next to the double bond, we saw allylic radicals and benzylic radicals. So seeing the double bond here should kind of jump out at you. Now, around the ring, we've got two hydrogens there. We've got two hydrogens there, two hydrogens there, two hydrogens there, two hydrogens there. Those are all secondary hydrogens. If you look at the carbons that they're attached to, all of those carbons have two other carbons on them. This carbon in orange has that carbon and that carbon attached to it. This carbon in red has that carbon and that carbon, etc., etc. So all of those carbons are secondary. So all of those hydrogens are considered secondary hydrogens, and they would give rise to a secondary radical if they were to be removed. There's one other alkane spot, and that's right there. That is a tertiary carbon that has one tertiary hydrogen on it. Again, that carbon has 1, 2, 3 attachments to other carbons, so it's tertiary. So that's tertiary. Now, it's not just tertiary, because remember that the space adjacent to the double bond means that it's also allylic. And allylic was even better than the tertiary. Of course, it's the same in this case. But if it were, say, secondary and allylic, it would be better than tertiary. The allylic property is more important than tertiary would be. So that's our hydrogen of interest. I want you to be careful, though, because these hydrogens in orange, you figure that here, that is one hydrogen, and there are two hydrogens there. Those are not alkanes. Remember that the definition of an alkane is it's got to be all single bonds. So since those are double bond, those hydrogens are on carbons that are double bonded, they're not considered alkane hydrogens. If you remember from our functional group slide, those are called alkenes. So those hydrogens don't react in the free radical chain reaction. You can only use alkane type hydrogens. So we're going to ignore the orange hydrogens there when we're determining which ones are reactive. We're going to ignore those orange ones. So the product that we get should come from removing the allylic, or in this case also tertiary, hydrogen. So we can get right to the product, or one of them anyway. So that product would look like this. We'd have the 6-membered ring. And by the way, you're going to get very good at drawing cyclohexanes in this class, hexagons, because 6-membered rings are quite common structures in organic chemistry. So we'll draw in our alkane, and in place of that tertiary allylic hydrogen, we're going to substitute the bromine. That is one of our major products. But remember, I said that there's another one. That's probably pretty tricky, because where would a comparable in energy hydrogen be? There isn't one. The secondaries are way too reactive when compared to the tertiary and the allylic. So how do we get the other product? Well, remember that the special feature of allylic and also benzylic hydrogens is that when they are removed, you get a radical that is resonance stabilized. So let's draw a mechanism to help us understand what's going to happen when we delocalize that radical with resonance. So I'll draw in our starting, actually, we have to start with, since we're doing the mechanism, let's start with Br2 in light, shall we? So we'll do that. Here's Br2. And that's going to react with light, H nu. And as a result of that, we're going to split this bond homolytically. One electron goes onto that bromine, one electron goes onto that bromine, and we get 2 Br dots, Br radicals. And again, that is our initiation step, just to keep track of everything. Okay, now we're going to take our alkane and I'm going to draw in our special hydrogen, the hydrogen that is going to react. And the way it reacts is that the bromine donates 1 electron, the hydrogen bond donates 1 electron, and the other electron gets put onto that carbon. Turn the corner here. So the result of that is our structure. But we've got a radical. So let's get to our first product first, and we'll worry about our second product in a moment. So in the next step, oh, by the way, this was our first propagation step. So I'll say P1 right there. And remember, in our first propagation step, our bromine radical reacts with the alkane to give us the carbon radical and also HBr. We'll draw that in just to be thorough. I'll put that in parentheses. There's HBr. So in the second propagation step, we're going to take our newly formed carbon radical. We're going to react it with an unsplit halogen. And we do that by taking 1 electron from our radical, 1 electron from our bond. Those come together to make a new bond. We split the bromine homolytically to give us a new bromine radical. And that explains the formation of our product. Our halogenated alkane there with our bromine substituted. In place of a hydrogen. And we also, importantly, make a new bromine radical. Perfect. We'll worry about a termination step later. First, remember, we need to figure out how we get this other product. Where in the world is this other product coming from? And I kind of led you into the mechanism because the answer lies in the mechanism. If you know the mechanism and you understand how resonance works, you will find that that leads you to the other product. So let's draw the resonance structure of this allylic radical. What I'm going to do, I'm going to copy our allylic radical. I'll put it over here. And let's draw the resonance structure. So remember how that works. You can go back and look at the notes, or you can go back and look at the book to see how we draw resonance. If you don't remember, we're going to take 1 electron from the radical, and we're going to take 1 electron from the adjacent pi bond, and we're going to make a new pi bond in that new location. Then we're going to take the remaining radical and put it on the other carbon. So let's draw what that looks like. We need our resonance arrow. not to be confused with equilibrium. I'll paste our structure again, but let's draw the new structure. So we moved our radical and we moved the double bond. So I'll get rid of our radical, I'll get rid of our double bond. Where is our double bond now? Well, it's here, right there. Remember that that's where the radical and one electron came together. They would go right between those two carbons there. So that's where our pi bond is. Where did our radical go? Well, it's this arrow right here. It put our radical on that end carbon. So now we have a radical on our end carbon. There we go. So remember that resonance structures are kind of two different ways to look at the same structure. So this means that we have some radical character on the tertiary site there, but we also have some radical character on the primary allylic site. It's primary, which you say, well, primary is not a good radical. That's true, but it is still allylic, and that makes it quite stable. So we got one product from one of the resonance structures. We should get the other product from the other resonance structure. Remember that there's radical character on both carbons. So either carbon could participate in this reaction. We get one product from one carbon, and we get the other product from the other carbon participating in the reaction. So let's go through and do our second propagation step using our new resonance structure. So we'll take Br2. Remember, the second propagation step is what gives us our product. So we should use that. And we're going to donate one electron from our radical, one electron from the halogen. That makes our new bond, but we also have to cleave the bromine to give our new radical. So what does our product look like? We'll take our new structure. Right there. And in place where the radical was, we add a bromine. So I got to draw a new bond. Be careful not to just draw in the bromine there, because now you've gotten rid of one of your carbons. We need to make the new bond. So there's the new bond. And that is attached to bromine. So there's our other major structure. There we go. I'm going to copy that. And we'll put it back up here with our first structure. There we go. So again, our first structure was formed from the radical in the allylic position, right there. But we can move that structure, we can move that radical because it's resonance. So this is where our radical would be also. So any carbon that has any radical character is susceptible to being substituted with a bromine. There we go. So just make sure we answered the prompt correctly. It says the following gives rise to two major products. Provide a mechanism to explain formation of both products. There we go. So here's our mechanism. We're going to do first our initiation step to make our bromine radical. Then we're going to do a first propagation step to transfer our bromine radical to our carbon to get the most stable radical possible. Then we're going to take our radical and we're going to add it to a new halogen to get our halogenated alkane. And you can finish with any termination step you want. So that's the end of lecture 6. The workshop from the Stramanis book is chapter 15, part A. There are lots of practice problems in there. There are also lots of interesting, useful energy diagrams to help you understand the energetics of this reaction more. There are lots of mechanism questions to help you understand the mechanism. Make sure you do the practice problems. It's super important that you understand this reaction. Again, this is the first reaction of hundreds that we will encounter in these next 12 weeks. So make sure that you get each one down as we go. Do not fall behind.